So now we're going to talk about the derivation of stiffness matrix for one-dimensional bar element. So let us take the bar element having a two node points. Let us say this is a node point 1 and this is a node point 2. So this node point 1 and node point 2 are the one-dimensional elements only. So if you say this is a simple generic uh, element of bar. So it has a two node point 1 and 2. At node point 1, it has a 1 degree of freedom, and similarly at node point 2 also it has having the 1 degree of freedom. Okay, so this is a very important things to know that one, how many degrees of freedom for each nodal point. Now, let us try to define the same element in a x coordinates. So means that I said that it is only 1 degree of freedom. So means that at nodal number 1, it has a 1 coordinate values. At nodal number 2, it is also having a 1 coordinate. Let us say it has a x directional element. So if we say that x directional element at nodal number 1, let us say the coordinate value would be equal to the x1. And let us say at node number 2, it has the x2 as a coordinate value. So x1 and x2 would be it is a elemental coordinate values at node number 1 and 2. So this is a simple generic element or bar element. So, and here let us assume the interpolation function for this one dimensional number. So let us assume, assume the interpolation function. So the interpolation function can be defined as it is equal to let us say that the q would be so at node number 1, if it is a x becomes x1, so let us assume that at node number 1, it has a displacement q1, and at node number 2, let us say it has a displacement q2. So therefore, it is possible to assume that the interpolation function that is called the q of x means that the q is the function of x. If x is changes, the q will go to change. And let us assume the interpolation function q of x is equal to the a naught plus a1 times x. So because if you take anywhere in the element, let us say this as a x. So at any rate, it is possible to say that the q of x interpolation function would be satisfied. So here, the a1 and a naught would be the two constant values. Let us try to find out the constant values in the form of the nodal parameters. So the q of x is equal to the a naught plus a1 x, and this is called as a assumed interpolation function. So therefore, at node point 1, at node 1, so the x becomes that, it becomes that x1. So therefore, the q also becomes that it is equal to the q1. So if you see that at node number 1, I said that it has x1 coordinates and the q will become q1. So if you write down the interpolation function at node number 1, it can be written as the q1 must be equal to the a0 plus a1 times of x1. Similarly, it is possible to write down that the what is a interpolation function at node 2. So at node 2, at node 2, so the x becomes that x2 and the q becomes that it is equal to the q2. So therefore, if you write down that here, the q becomes that q2 must be equal to the a0 plus a1 times of x2. Let us say this is equation number 1 and let us say this is equation number 2. And let us try to do that 2 minus of 1. If you do the 2 minus of 1, therefore, it is possible to write down that the q2 minus q1 must be equal to the, because this is a q2 and here minus of q1, this place becomes a minus 1 and q2, sorry, a naught get cancelled. So therefore, you're going to get that a1 times of x2 minus x1. So this is a value. Once you do that, the 2 minus 1. So this q2 minus q1 would be this one. And from this one, it is possible to say that that is equal to the constant value of a1. The a1 can be defined as it is equal to the q2 minus q1 by x2 minus x2 minus x1. So this is a constant value a1. Similarly, we have to find out the what is the a naught value, and let us substitute into the equation number 1. So therefore, it is possible to say that the q1 would be equal to the a naught plus, and if you substitute that, the a1 is equal to the q2 minus q1 divided by the x2 minus x1 times of x1. If you substitute this a1 into a, substitute that a1 into equation 1. So therefore, the equation 1 can be rewritten as it is equal to the q1 is equal to a naught plus q2 minus q1 by x2. And this can be written as q1 is equal to the, and just you have to take the LCM. So therefore, it is possible to say that, or otherwise, instead of doing the LCM, let us take that the a naught would be equal to the q1, just send to other side, it becomes the minus of q2 minus q1 by x2 minus x1 times x1. Okay, so here the a naught can be written as from the above equation. You take that LCM, therefore q1 times x2 minus q1 times of x1. Okay, so therefore then it is possible to write as minus into plus become that the q2, and q2 you have to multiply with the x1, therefore q2 x1 and this plus q1 x1 and divided by the x2 minus x1. So here minus q1 x1 plus q1 x1 get cancelled. So therefore a naught can be defined as it is equal to the q1 x2 minus q2 x1 q2 x1 divided by the x2 minus x1. So this is the two constant values that we're going to get from the what is that, from the above cases. Now let us try to substitute this a naught values and a1 values into the interpolation function. Let us say this was called as a assumed interpolation function, and now substitute a naught and a1 values into a interpolation function. So if you substitute that one, therefore the q of x can be written as it is equal to the a naught would be I got that q1 x2 minus q2 x1 divided by the x2 minus x1. Okay, x2 minus x1 plus a1 times of x. So here a1 I have calculated that it is equal to the I got that a1. So let us see that the a1 would be equal to here q2 minus q1 by x2 minus x1. So substitute that one here, and it can be written as q2 minus q1 and divided by the x2 minus x1. So here q2 minus q1 divided by the x2 minus x1 times of x. Okay, so now let us take that the common as a x2 minus x1, or otherwise let us separate the q1 terms and q2 terms. If you do the separation of the q1 terms and q2 terms in the above equation, therefore it is possible to say that there is a here the q1 times of x2 is there, so therefore q1 times of x2, here the q1 times of minus x is there. and divided by the x2 minus x1, x2 minus x1. So this is a means that I'm separating the what is the q1 terms as well as q2 terms. So if you separate the q1 terms and q2 terms, the q1 terms will be x2 minus x by x2 minus x1. And similarly here also you're going to get that the q2 terms are the q2 is multiplied with the x1 and here it is equal to the x only. So therefore this can be written as x minus and x1 divided by the x2 minus x1. So this is the what is that the separation terms from the above equation. So from the above equation, it is possible to say that the q would be the function of the q1 comma q2, q1 comma q2. So I have written that the q of x in the form of q1 terms and q2 terms. So here I can able to write down this q of x in the form of the shape functions also. So let us try to write down that, and I can say that this would be called as a, let us say n1, and I would like to call this as a n2. So where n1 and n2 are the shape functions. I can call this as a shape functions. So the shape functions can be defined as n1 is equal to x2 minus x divided by x2 minus x1. So instead of writing that one, I would like to write up n1 and into q1 plus n2 into q2. So here the n1 and n2 are the shape function. So this is a simplification form. Now let us try to define the what is a strain developed. What is a strain? What is a strain developed? What is a strain developed? What is a strain developed in a bar element? So in the above we have taken as the bar element. Okay. So what would be the strain that is developed in a bar element? Let us try to define that. Now what is the strain that is developed in a bar element? Okay. So the bar element having a nodal number 1 comma 2. So in nodal number 1 comma 2, I would like to define what is a strain which is developed in this one. So the strain can be defined as it is equal to the change in displacement. We can say the q of x. We have to differentiate the q of x with respect to the distance x. Okay. So if you do the differentiation of the q of x and q of x with respect to the x, you're going to get the strain. So the strain developed can be defined as it is equal to the strain can be defined as epsilon. So for a bar element, the strain can be find out it is a differentiation of the displacement function with respect to the variable dx. If you do the differentiation of above equation with respect to dx, you're going to get the strain. Let us do the differentiation of dq of x with respect to the x. If you do the differentiation, therefore the strain can be defined as in this one x2 by x2 minus x1 times of q1. It would be equal to the there is no x terms, therefore it can be possible to say it is 0. So only minus x by x2 minus x1 into q1. There is a possibility of x variable is there. So here you can observe that the x2 and x1 is not a variables, it would be the constant. Only the variable would be the x only. The variable would be the x only. So means that you are going to differentiate the q of x with respect to the x only, not with the x1, x2. Okay. So only you are going to differentiate the variable x only. If you do the differentiation, the first parameter you are going to get that minus of q1 by x2 minus x1. Then next one would be going to get that you're going to get that plus 1. The x differentiation would become that 1. This would be q2 by x2 minus x1. So this is the strain values that you're going to get. So let us take this as this is called as a linear equation. Now, I would like to transfer this linear equation into a matrix form. So I can able to transfer that epsilon can be read as, I would like to take Q1, Q2 would be a column matrix. So therefore, I can able to say that there is a two rows and one column. So therefore, I would like to write down this matrix. So this matrix can be write as, if you take that Q1 as common here, so the remaining would be the minus 1 by x2 minus x1. The next parameter would be it would be 1 by x2 minus x1. So let us recalling the element again. So in the very first I said that this is a nodal number 1 and nodal number 2. At nodal number 1 I said that there is x1. At nodal number 2 it is x2. So therefore the x2 minus x1 would be called as a length of an element. So this is can be called as it is called the length of an element. So the length of an element can be defined as L suffix e. So here the L suffix e is called as a length of an element. So therefore it can be replaced that x2 minus x1 can be 1 Le. So therefore it is possible to write as minus 1 by Le comma 1 by Le. So this is called as a row matrix only. There will be one row and two columns and into Q1, Q2. So here, if you see that the Q1 and Q2 would be the 2 by 1. So if you multiply that 1 by 2 into 2 by 1, you are going to get the only one equation that is called the linear equation. So what I done here, just I have transferred the linear equation into a matrix form. Okay, so this is a matrix form. Now again, I would like to simplify this one. Okay, so if you want to simplify that above strain equation, therefore I can able to simplify this one. I would like to take as 1 by E as a common, and it can be possible to say that minus 1 comma 1 and into Q1 by Q2. So this would be the strain formula for a bar element having a nodal number 1 comma 2. So now at this point of time I can able to say that this matrix is called as a B matrix. B matrix, and this matrix is called as I can say it is called nodal displacement matrix. Nodal displacement matrix. So nodal displacement matrix. So therefore, it is possible to write down that the strain is equal to the strain, the strain epsilon can be written as B matrix into the nodal displacement matrix. Let us say it is equal to the U. Okay, or otherwise small q. Okay, so nodal displacement matrix would be, let us say it is equal to q. So here the B matrix range would be right is equal to 1 row 2 column and q would be the 2 by 1 column. This is a strain formula for a simple generic element having a nodal number 1 comma 2. Okay, so this B matrix is very useful to derive the stiffness matrix in the next session. And also we can able to find out the stress. The stress can be defined as it is equal to the sigma. The sigma is directly proportional to the strain, or otherwise sigma is equal to the Young's modulus into the epsilon. So therefore the stress in a simple generic element can be defined as Young's modulus into epsilon can be written as B matrix into the Q matrix. So this is a stress formula, and using this stress formula, it is possible to find out what is the stress developed in a bar element. So for example, two bar elements is there. We are going to use the same formula, but the notation is going to be changed. So this is all about the what is that? The stresses and strains. Now, so once you found the stresses and strain, now let us focus on the how to derive the stiffness matrix for a simple bar element. So in the previous slide, I have taken that the simple generic bar element nodal number 1 comma 2, and it is a simple element. So for this simple element I have written that epsilon, right, it is as B comma Q matrix, where Q is equal to the nodal displacement matrix, and at node number 1 it has a Q1, at node number 2 it has a Q2. So therefore, the nodal displacement matrix can be defined as it is equal to the Q1, Q2. And similarly, from the previous slide, the B matrix I have written that it is equal to the 1 by E or minus 1 by LE, comma 1 by LE. That LE is nothing but length of an element. Okay. So using this matrix, now I would like to find out what would be the stiffness matrix. And let us recalling the strain energy from the potential energy equation. The strain energy formula from the potential energy equation. Potential energy equation. So if you're recalling that the strain energy is equal to the strain energy, let us say or otherwise strain energy can be defined as it is equal to the integral of or half into integral of sigma transpose into epsilon into dV. Sigma transpose into epsilon into dV. So from this one, it is possible to write as the sigma can be defined as it is equal to the, I know that sigma is equal to the Young's modulus into epsilon. So if you substitute here, that is equal to Young's modulus into epsilon to the power of transpose into epsilon into dV. So again, if you further simplify, therefore half into this E into epsilon to the power of transpose can be defined as it is equal to the epsilon transpose into Young's modulus into epsilon into dV. Now again, the epsilon transpose, epsilon can be defined as it is equal to the B matrix into Q matrix. So this we have derived in the previous slide. So if you substitute that one, therefore half into integral of this is can be written as B matrix into Q matrix to the power of transpose into Young's modulus. The epsilon can be written as again it is equal to the dq form into dV. So where dV can be also written as it is equal to the area into dx. Area into dx. If you substitute that one in the above equation, this can be written as half into dq transfer can be written as integral of q transpose into b transpose into Young's modulus E into b into q, where dV can be replaced as a area into dx. So now I'm going to derive what is a stiffness matrix for a bar element. So bar element, the volume can be defined as area of that element into the dx, because after all it is a one-dimensional member. So this equation can be written as the half is again constant, and this q transpose q is called as it is a nodal displacement matrix. The transpose also it is a 2 by 1. Then after doing the transpose, it is getting that 1 by 2. This is called nodal displacement matrix. So the nodal displacement matrix would be the constant matrix. So take out that outside q transpose. Okay. So q transpose, and there is called b is it is called minus 1 by LE. Okay, into LE. So that also you have to take constant and take that as a b transpose outside. And also Young's modulus is a constant, again you have to take that is also outside. And the b is also again it is a constant, you have to take that outside. And into area is also constant. Okay, take it outside. Okay, and integral of dx into q. Again the q you can take that as a outside because it is also constant. Okay, so integral of dx, and the dx can be having a limits of from the 0 to m. So length is varying from the, let us take that if the length is starting from 0 and ending with a length of an element. So if you substitute this one, you're going to get this one. So therefore from this one, the strain energy can be defined as is equal to the half into q transpose into b transpose into epsilon into b into area times of Integral of dx can be defined as it is equal to the L only. If you do the integration of dx, you're going to get that x, and where x is 0 to L, if you substitute this one, you're going to get L. So therefore, the Q will be present. And this can be write in a terms of half into Q transpose into stiffness matrix K into Q. Since I would like to say the K would be is equal to the B transpose into Young's modulus into B into area into L. So if you multiply this one, you're going to get the stiffness matrix. Let us do the multiplication. So if B is this one, so therefore I can able to get as B transpose is equal to the minus 1 by LE and 1 by LE. Means that we are going to change that rows into columns. So therefore the K can be find out, the B transpose is equal to minus 1 by LE, again 1 by LE, and there is a Young's modulus is there. Okay, let us take Young's modulus as it is. So Young's modulus and E and L both are the single parameters. So take that A and E and into L outside. Again B matrix, that B matrix is equal to the minus 1 by LE comma 1 by LE. So means that only we have to multiply the B transpose into B. So here the B transpose would be the two columns and one, so two rows and one columns, and here it is a one column and the, sorry, one row and the two columns. If you multiply 2 by 1 into 1 by 2, you're going to get that 2 by 2 matrix. So let us try to see that how much the 2 by 2 matrix. Okay, so minus 1 by LE into minus 1 by LE. So you're going to get that 1 by LE square. And next one minus 1 by LE into 1 by LE. So you're going to get that minus 1 by LE square. And the third parameter 1 by LE into means that this row into column and second row into column. So like that 1 by LE into uh, minus 1 by LE. So therefore, you are going to get that 1 by LE square. The last one would be, or this would be the minus and plus would become that minus sign, and last one again it is a 1 by LE square. So here into you're going to get that AE by N. Now I can able to take the 1 by L square as a common from the above one. So therefore, in the stiffness matrix, it is possible to take the common 1 by L square. If you take the 1 by L square as a common, so therefore the stiffness matrix K can be defined as it is equal to the AE into L, and let us take that L square as a common there into, if you take 1 by L square common, so it becomes that 1 minus 1 minus 1 and 1. Okay, everywhere you are going to take 1 by L square as a common. This L square get cancelled, so it can be rewrite as it is equal to the AE by L into 1 minus 1 minus 1 1. So this would be the stiffness matrix for the bar element. And here let us try to assume that the since, okay, let us try to assume that the AE by L can be called as a small k. So if you assume that one, therefore it is possible to write down the stiffness matrix. The stiffness matrix can be write as the k would be equal to the, it is a previously it is equal to the AE by L into 1 minus 1 minus 1 1. So this can be write as, because I have assumed that the AE by L would be equal to the small k. So if you do that one, therefore, if you multiply A by L with each and every element, therefore, it can be written as small k minus small k and minus small k, where k is equal to the stiffness of stiffness that is equal defined as AE by L. So therefore, for simple bar element, the stiffness matrix would be the, it is equal to the 2 by 2 matrix. It has a k minus k minus k k, or otherwise it is defined as AE by L into 1 minus 1 minus 1 1. So this is the formula for the simple bar eliminated. Thank you.